Hey guys, it's Mr. Chemistry here. Today we're going to be reviewing for acid and base test. And here we go, let's jump right in. First question, I did not react with a metal. Okay, so here's the thing. The thing about acids and bases is that acids dissolve, right? It dissolves metals, right? That's why the fact that it did not react with a metal, it tells me that it's a base because bases do not dissolve metals, okay? All right, let's move on. I stayed clear when phenolphthalein was added. All right, so the thing about this chemical here is that it's an indicator, right? Write that down, indicator, and it reacts positive with bases only, okay? So the fact that it stayed clear, it tells me that it has tested negative against this solution. So I can actually assume that this solution is an acid, right? Because again, if it does react with if it does react with a base, it turns pink. That's the color. All right. The way that I like to remember phenolphthalein, P is for pink. Okay. All right. So let's move on. I turned orange with universal indicator. Okay. So universal indicator is kind of like it's a litmus paper, right? It measures the pH level of an unknown solution. And there's a wide spectrum of colors, right? It goes from red all the way to blue/purple, right? And this is where the acid is, and this is where the base is, right? Right down the middle, green is where the solution is neutral, okay? So the fact that it's turned orange, now orange is going to be somewhere around in this area, right? So that tells me that it's an acid. Anything to the left of the neutral green is an acid, right? So this solution is going to be an acid. All right, let's move on. I turned blue. Now, blue is the other side of the spectrum, right? Blue tells me that it's probably somewhere around here, making the solution a basic solution. Okay? All right, so those were some of the properties. A quick thing about acid is that you should know that acids are sour, right? That's why when you're sick and when you vomit, disgusting, sorry, it's got that sour taste in your mouth, right? Because acids are sour. And what do you have in your stomach? A lot of stomach acid, right? And base is going to feel, not feel, but taste, I want to say bitter, slippery. Okay, those are some examples of a base. Okay, so let's move on. So here's some pH calculations, okay? Now, I know that what we have here, guys, it's very intimidating with a lot of numbers. But just remember this, guys. A pH plus pOH should always equal to 14. All right? So I'm going to use that and tackle these questions, okay? So I know that pH is 5. So I can already, you know what? What's 14 minus 5? 9. That's my pOH, right? Because they both have to add up to 14. All right, so now with this given information, what do I have to do? Well, there's two ways of doing these questions, okay? So what you could do, you can actually use an equation that ties pH and the concentration of H plus together. And that is going to be this one, right? If you're trying to solve for the unknown, which is the H plus. So if you were to plug that in to your calculator, okay, so 10 to the power of negative 5. Now, where am I getting this negative 5 from? Well, that's my pH level. Just put a negative in front, right? And what's going to show you is that it's 1 times 10 to the negative 5th power. Okay, so let's put an M molarity because that's an actual concentration. Okay, and here's another quick tip, guys. If you look very closely, there's going to be a pattern between the pH and the H plus concentration. This 5, guys, is an inverse of this exponent here. Okay, if you don't know what an inverse is, it just means the opposite, right? If it's a negative, then it's a positive. So if you look at this negative 5 here, guys, what's the inverse of this negative 5? This 5 here, the positive 5. Okay, so know the relationship between the two. Okay, now if you have doubts in yourselves, you can just pull out your calculator and double check your work. Okay, now the same rule applies here as well for the POH. So that 9, you can actually go 1 times 10 to the power of 9th power. Okay, so once again, this 9 and this negative 9, they're related. Okay, all right, so let's go ahead and see if this solution is acidic, basic, or neutral. Well, I am going to focus right on this number only. pH, that is 5. Well, we know that pH of 7 is neutral. Anything to the left, anything that is less than 7, it makes it, the solution, acidic. So this tells me that this solution is an acid. Okay? All right, why don't we go ahead and do one more question here. I want you to go ahead and try the last one by yourself here, the row, okay? The last row. So here's row 2. I got POH. I'm going to go ahead and quickly find out what my pH is, which simply can be done by 14 minus 9. Boom. 5. Oh, wait, what do we have here, guys? 2 of the same. Okay. Well, let's not worry about this question then. Let's not worry about this question. Why don't I change it up a little bit and say that the POH is 10? Okay, so again, same thing. 14 minus 10 gives me 4. Okay, so with given pH and POH, I can go ahead and find what the missing concentrations are, right? So again, you can actually plug it into the equation and use your calculator, or what you could do is just boom, there it is. Shortcut, right? Again, that number and that number, they should be inverse of each other. Likewise for this one, boom, done. This 10 and this 10 up here, inverse. Okay, now let's see if the solution is acidic or basic. Let's look at my pH here, guys. It's 4. Once again, the pH is smaller than 7, right? Which tells me that it's an acid. Okay? All right, so let's move on forward. We have Arrhenius reactions. What does that really mean? It means when an acid or base is dissolved in water, it dissociates, which it's a fancy way of saying it separates. Okay, it breaks down in half. Water can break down acid and base in half. Here's what I mean by half. KOH, that is potassium hydroxide. Just from the look of this reaction, this chemical substance, I know that it's a base because it has OH, hydroxide in it, okay? So I'm going to go ahead and draw a vertical line here, and that's where it breaks. Okay, that's where the compound dissociates. So now K by itself is going to be a K plus. Okay, if you're thinking, wait, where'd you get that charge from, Mr. Chemistry? Well, refer to your periodic table. Potassium is a group 1 metal, which means it has a charge of a 1 plus. That's where I'm getting that plus charge from, okay? And here's aqueous. Don't forget about the states of matter, okay? And what's the other side? What's the other half? OH minus. That would be the hydroxide. Also aqueous. Now, if you're also thinking, where'd you get that negative from? Well, if you look on the back side of your periodic table, you'll find that hydroxides have a 1 minus charge. And that's it, okay? Now, I'm going to go ahead and write this on the side note. Say that this is a basic solution. How do you know? Because, boom, the presence of this OH minus hydroxide makes the solution basic. Okay? All right, moving on forward. Let's see, I got calcium hydroxide here. Again, it's got the hydroxide making this a basic solution. So where does it break down in half? Right here. Okay, so let's go ahead and break that down in half. Calcium is going to be by itself. Now, if you look, periodic table, it's a group 2 metal, all right, which means it has a charge of a 2 plus. Don't forget about the state of matter and plus. Now, here's the thing, guys. OH minus, right? That's the hydroxide. Let's go ahead and write down the state of matter. But this time, you need to make sure everything is properly balanced. Right now, it's not. Because if you look on the left side, there's two sets of OHs, right? Two sets of hydroxides. But if you look on the right side, as my product, there's only one. So please use your coefficients. Put a 2 in front, and now we're good to go. Everything is balanced. 1 calcium on both sides and 2 hydroxides on both sides. Good to go. This is also an example of a basic solution. Why? Because the presence of this hydroxide makes it basic. Moving on forward, okay? So here's more Arrhenius reactions, but this time it looks a little bit different, and I'll tell you why. Because do you see hydroxides anymore? No, I don't. So these are not bases, but instead, I can recognize that this is an acid. How do I know? Because it's got hydrogen in front. Okay, so let's see how this dissociates in water, how it breaks down in presence of water. So water is going to do a really good job breaking this down right down the middle, right over there. Now let's go ahead and see what the broken up parts are, okay? H plus, going to be by itself. Why does it have a 1 plus charge? Because hydrogen, it's in group 1, right? Which making it 1 plus charge. I'm going to bring over the aqueous state of matter, and I'm just left with NO3 minus, okay? That's nitrate. How do you know, Mr. Kim? Well, because if you look on the back side of your periodic table, this is a polyatomic ion with a 1 minus charge. Okay? Another quick way of looking at this, guys, is that what ratio are the two combined in? It's 1-to-1 ratio, right? So which tells me that if there's 1 hydrogen, then there should definitely be 1 NO3, okay? All right, looks like everything is already balanced. Okay, now on a side note, I'm going to say that this is acidic. It's an acid. Why? Because the presence of this H plus ion makes the solution an acid. Okay? All right, let's move on. Okay, this one's a little bit different. It's okay, we'll get to it. Break down in half, H plus aqueous, same thing, and CO2. Oh, that is not CO2. Guys, I'm sorry, that's a typo. This should have been a 3. Okay? Alright, sorry about that. CO3, 2 minus. That is carbonate. This is a polyatomic ion, which is on the backside of your periodic table. It has a charge of a 2 minus. Okay. All right, so what do I need to do this time? Well, I'm going to put a 2 in front because there's not enough hydrogens on the right side. Now it looks pretty good, right? There's equal number of hydrogens and there's equal number of carbonates on both sides. Everything looks great. Also, this is acidic. It's an acid. Why? Because of the presence of this H plus ions, okay? Okay, zooming through here, we got Bronsted-Lowry reactions. Now, I'm going to do one question here, okay? So the thing about Bronsted-Lowry is that you just need to remember that acid donates 1H plus to the base, okay? So let's go ahead and see what happens, what occurs here, guys, okay? So here's the thing. I can see that this is an acid. Why? It has a hydrogen in front, okay? And then what does that make this water here? Well, this water is now going to be a base, okay? I hope you guys remember this, but water is a really, really unique molecule. We call it's an amphoteric molecule, which means it can be both an acid and base, right? So this time, this water is going to act as the base, and it's going to receive an H plus from this acid. Okay, so it's going to take this hydrogen and boom, it's going to give it to that water. Okay, so let's see what happens here, guys. Now that F has a negative charge because it lost 1 hydrogen. That's why it has 1 more of the negative charge. Okay, now we call this a conjugate base. Okay, these two are related, right? Why is it a conjugate base? Because before it was an acid, but because it lost one hydrogen, it became a little bit basic. Okay? All right, let's go ahead and give it the state of matter. And what about that water? That water has an additional H plus. Okay, so now it makes it H3O with that plus. Don't forget about that plus, guys, okay? All right, write that down. And now we call this a conjugate acid, right? Goes from here to there. Those two are closely related. And I think I'm done here. Yeah, everything is correctly balanced and we're good to go. Okay, so try the next one by yourself, guys. Now the order is going to be a little bit different because this time we have an acid on this side, right? Because this has that hydrogen, it's going to donate that H plus to this OH minus, okay? Which making it water, right? That's going to be liquid, and NO3 minus, like so. Okay, sweet. Let's move on forward. Okay, so here is neutralization reaction. Okay, so what does that mean? It means when you add an acid and base, okay, you produce water and a type of salt. Let's go ahead and do one example. I'm going to show you what I mean by that, okay? All right, so here is what we have. Before I do anything, guys, when it comes to neutralization reactions, I like to label all my charges. This Mg is going to be a 2 plus, right? How do I know? Periodic table. It's group 2 metal and it has a 2 plus charge. The thing about hydroxide, it has a 1 minus charge, right, guys? All right, so what about hydrogen? It's got a 1 plus and chlorine is going to be 1 minus, right? So now the thing about this is that they will switch places, right? So the metals and non-metals will switch places. So this metal is now going to react with this chlorine, okay? Now, could they react in 1-to-1 ratio? I'm afraid not, because if you look, Mg is a 2 plus, Cl is a 1 minus. They need to make sure that the charges are neutralized, right? Gone. So they're gonna have to combine in MgCl2. So 1-to-2 ratio, right? To make the charge go away. All right, so let's go ahead and get rid of all of that. Don't need that anymore. And what about the other ones? Well, this hydrogen and that hydroxide is now going to react to form, boom, water. Okay? All right. So now let's make sure everything is balanced though. All right? That's my final job here. Looks like I got 2 hydroxides. Okay. 2. Oh, okay. So if I put a 2 in front here and 2 in front here, it looks like everything is fully balanced. Yep. Looks good. All right. So here's what I mean by here's the water that's created, and here's the salt. We call anything ionic compound a salt. So that's what that is, okay? All right, let's push through, guys. One more equation. All right, so we got some titration equations now, okay? So I know this looks really intimidating. Wow, there's a lot of variables. Honestly, it's a lot easier than you think, okay? Here's step 1. Always determine the moles of H plus and moles of OH minuses first. Let's go ahead and work that out, all right? So we got an acid here, H2SO4, okay? Now, how many H pluses are here in this acid? If you look here, guys, it says 2, right? So the coefficient for this is simply going to be 2. That was easy, right? But what about KOH? What's the number of moles of OH minuses that's created from KOH? Well, if you look here, there's only 1. So my coefficient is simply just 1 for that. All right, so let's go ahead and just kind of draw a vertical line there. Now, I'm going to go ahead and rewrite this really quick. Here's an acid, volume for acid. Here's the number of moles of OH minus, molarity of B for base, volume for base, okay? make sure that these volumes are in liters. Always. Okay? All right, here we go. So the coefficients that we found, right? So that's a 2 times, what's the molarity of this acid here? What is the concentration? Okay, so we're trying to find the concentration here, which is the molarity, okay? That means molarity. So that's my X, what I'm trying to find. And volume of acid. Okay, it tells me 50. I cannot just put in 50. Why? Because it is in milliliters. So if you do 50 divided by 1,000, that gives me 0.05. Okay? And the number of OH minus, wow, that does not look like OH minus. Better. Okay, so the coefficient is 1, right? We found that. Let me just color code that so that people know where I'm getting these numbers from. That 2 is, that 1 is that, okay? Molarity of the base, it tells us that is 0.20. Times, what's the volume here, guys? It's 10 mils, right? 10 divided by 1,000, that gives me 0.01. Done, guys. That was so easy. Now solve for X. Okay? So I'm going to work out the right side. And my X is 0.02. That is M for molarity. And that is it, guys. That was easy, right? All right. Happy studying and good luck.